Welcome back. In the next part of this section, we're going to start talking about solving logarithmic equations. And same thing before as with the exponential ones, I'm going to start with the easier ones and then work my way up to more complicated problems. There is one plot twist here. For the exponential equations, you'll notice I didn't bother checking any of my solutions for those. And that's because we don't have to worry with exponential equations about having extraneous solutions. Unfortunately, for logarithmic equations, when we solve them, it's possible that there might be extraneous solutions. In the same way that when we were looking at radical equations, there might be extraneous solutions. So, important thing for us to remember here is that anytime we're solving a logarithmic equation, we really should be checking our solutions because it's possible that one or more of them might be extraneous. So let's take a look at doing some solving. And for each time that I solve one of these equations, I'll have to do some work on the side to check my solutions. First kind of equation that we might have, the easiest one, is sort of like for the exponential one when it was two exponentials with the same base. Here we have two logarithms with the same base. And if you have two logarithms with the same base that are equal to each other, then you can conclude that their inputs, that their insides, must be equal. So if we can get that equation in that form of one log with a base equal to another one with the same base, then we're kind of on easy street. So let's take a look. This one, again, the key thing is can be written. It's not that it's already going to be given to you in that form, and here we're not in that form yet. We don't just have a logarithm on the left side, you have 2 times a logarithm. And you don't just have one single logarithm on the right side, you have one log minus another. So maybe we might have to do a little bit of work as far as the solving goes, as far as doing some cleaning up first before we can apply that approach. So in this case, I'm going to use my properties of logarithms and say that the 2 times the logarithm could be brought up as an exponent. So 2 natural log of x minus 1 becomes natural log of x minus 1 squared. And natural log of 18 minus natural log of 2 becomes natural log of 18 divided by 2, which is the same thing as natural log of 9. Okay, so now I've got one natural log equal to another natural log, so I can conclude that the insides, the x minus 1 squared and the 9, must be equal to each other. And so now I can go ahead and check my find my answers. If I wanted to solve for x, I could take square root of both sides, and of course it would be plus or minus the square root. So x minus 1 is plus or minus 3. And that's going to give me 2 possible values for x. I'm going to have x being positive 3 plus 1, or in other words, x is 4. And I'm also going to get x is negative 3 plus 1, or x is negative 2. And I can't just stop there and say, there we go, those are my solutions. I'm going to need to check my solutions first, because it's possible that one of them or both of them might be extraneous. So here when we're checking, again, it's important, just like it was with radical equations, we're not going to check in the last line or the last couple of lines. We need to check to see in the original equation, because that was what we were trying to solve, which of these values, if either of them, makes this into a true statement. So let's check this x equals 4 and x equals negative 2 and see what happens. If I'm going to start with checking x equals 4, I need to put in 4 into the equation, the original one. The left side is 2 times natural log of 4 minus 1, which is 2 times natural log of 3, which becomes natural log of 3 squared, and that's just natural log of 9. The right side is just going to be natural log of 18 minus natural log of 2. No place for me to put in an x value there. But of course that simplifies to give me natural log of 18 divided by 2, which is natural log of 9. So left side and right side are equal to each other, and I can feel happy about that. So 4 definitely is a solution, but good question. What about negative 2? The right side is going to be the same as before. Since the right side didn't have any x's for me to put in, then the right side is going to be, as always, natural log of 18 minus natural log of 2, and that'll simplify to give me natural log of 9. The left side, on the other hand, if I put in negative 2 for x, I'll have natural log of negative 2 minus 1, which is 2 times natural log of negative 3. And unfortunately, this is where we have to stop because natural log of negative 3 is undefined. Remember, for any kind of a logarithm, no matter what base you're looking at, you can't have a number 0 or smaller as the input. Natural logs, the inside of what goes into them, or any other log for that matter, has to be larger than 0. So since natural log of 3 is undefined, the left side is undefined, which means the left side and the right side will not be equal to each other. And so too bad for us, that means we need to reject x equals negative 2. So our only solution for this problem would be x equals 4. Now, I know one little comment that people are going to be thinking in their minds, or a question that they're going to have is, couldn't we work around that? Couldn't we fix our problem by bringing the 2 up as a power, and that would make us square the minus 3, so it would now be a positive? Except, unfortunately, no, we wouldn't be able to do that because if we have a line that's undefined, you can't undo that and make it suddenly a defined thing. So if we ever reach a problem where things are undefined, unfortunately, we can no longer apply our log properties. Log properties would apply, so bringing 2 up as a power would be something possible to do with a log that is defined. So if this was log of a positive 3, we could certainly bring up the 2 and square it. But since natural log of negative 3 is not a number, we can't apply that log rule to it and bring the 2 up as a power. That's why we have to stop there. That's also why it's important for us to be checking with the original equation. If you were to check by putting 4 or negative 2, for example, into the third line in or the fourth line in, it would certainly make it a true statement. But unfortunately for the original equation, putting in a negative 2 would make this natural log undefined, so therefore you wouldn't be able to have any of the other further steps. So, big moral of the story here for logarithms, we have to always be cautious and think about the fact that we're going to need to check our solutions. And we also are going to have to remember to check our solutions in the original equation. Just as a little side note, the fact that negative 2 is being rejected shouldn't be a surprise to us, because if we were thinking about the function y equals natural log of x minus 1, that's a log function that's been shifted to the right by 1. You know, for that function, the domain would be only things that are larger than 1, which means that if you put an input for x that was 1 or smaller, you would be undefined, and that's why negative 2 happened to be rejected. It's a number that's not in the domain of that logarithm, which is why that logarithm was undefined. Okay, so next one up. Another approach we might have is maybe you don't have one log equal to another. Maybe you have one log equal to a number, and in that case you can just rewrite it as an exponential equation. And in fact, we've done that before at the very beginning of logs in 6.3 even. Again, the key phrase here is can be written, so maybe it won't already be in that form. Maybe you'll need to put it in that form. And that's what we've got going on here. On the left side of the equation, we have 2 logs, both with base 3 added to each other. So it's not just one log equal to a number, it's 2 logs added equal to a number. But good news for us, since these both have the same base, then I can use one of my properties for logarithms and say that it should be log base 3 of these 2 insides multiplied together, log base 3 of x plus 2 times x minus 6. That should be equal to 2. And if I wanted to just expand that, that would be log base 3 of x squared minus 4x minus 12. Equal to 6. Or sorry, equal to 2 rather. And now that I've got one log equal to a number, I can rewrite this as an exponential equation. So instead of log base 3, it'll be 3 to the power, and we'll switch our inputs and our outputs. And I've got 9 equals x squared minus 4x minus 12. Or if I bring the 9 to the other side, I've got x squared minus 4x minus 21. And numbers that multiply to negative 21 and add to negative 4 would be negative 7 and positive 3. So we come up with our two values for x, our two potential values, 7 and also negative 3. And same thing as before, we're going to have to check our solutions because it's possible that one or both of these might be extraneous. So if I'm going to do that again, I need to make sure that I'm checking in the original equation, not in one of the subsequent lines, because we want to know, does the original equation get solved by 7? Does the original equation get solved by negative 3? So let's check our work. And here I'm going to check, and the nice part is, of course, the right side is already done for us. The right side is always just going to be 2. So the question is, what's going on with the left side? I'm going to start with checking x being 7, and then I'll do the negative 3 afterwards. Okay, so we have log base 3 of x plus 2 and log base 3 of x minus 6. So log base 3 of 7 plus 2 and log base 3 of 7 minus 6. So that becomes log base 3 of 9 and log base 3 of 1. And both of those we can evaluate. 3 to what power gives me 9? The answer is the power is 2. 3 to what power gives me 1? The answer is the power is 0. And 2 plus 0 adds to 2, which is my right side. So therefore, left side is equal to the right side. And definitely 7 must be a solution. If we're checking the other possible solution, and the other solution that we had was negative 3, the other possible one. Same thing as before, right side is always just 2 in this equation, and in the left side, if we put in negative 3 for x, we'll have log base 3 of negative 3 plus 2, and log base 3 of negative 3 minus 6, which gives us 2 logs, and actually, unfortunately, both of them are undefined. Even if only one of them was undefined, that's enough for us to stop right there. Log base 3 of negative 1 is undefined. Log base 3 of negative 9 is undefined. So too bad for us. We do not have left side equal to the right side, and we need to reject x equals negative 3. So that means the only solution that we have to this equation would just be the single number 7. Same thing that I said for the last example, because I know somebody out there is thinking, couldn't I just say that this is now log base 3 of negative 1 times 9 and that'll fix my problem? And the answer is no, it won't fix your problem, because to use a log property, you'd have to have logs that were defined. If it was a positive 1 and a positive 9, you could certainly combine these two logs together, but because this first thing is undefined and this second thing is also undefined, you can't combine them together to suddenly make them defined. So that's too bad for us. Once we find that a log is undefined, we just have to stop there and say that that's it. The left side and the right side will not be equal to each other. Let's do another one. This one you'll notice there's no base given, so that means we are talking about log base 10. And same sort of a thing as the last one. I can see that I've got one log minus another, so I can definitely combine those two logs together. That would be log of 9x plus 19 over x minus 8. equals to 2. So now I've got log of one thing equal to a single number, and I can rewrite that as an exponential equation, and since this is log base 10, then it's going to be exponential base 10. So 10 squared is equal to 9x plus 19 over x minus 8. And now I just need to continue solving. So I'm going to square the 10. I'll bring up the x minus 8. And I'll have 100x minus 800 equals 9x plus 19. And now all I need to do is continue by first bringing the 9x to the left side, and then bring the 800 to the other side. So I'll have 91x equals 819, and then divide by 91. And when I divide by 91, I get 9. Now, you might be tempted to just say, hooray for us, we found only one number, so therefore it must be the solution. But unfortunately, there's no guarantees that it actually is the solution. And a log equation very well might have no solutions at all. So even though there's only one solution or one thing that we think is a solution, we still need to check. So if you just stop there and say, the answer must be 9 because I only found one thing, you might be making an assumption that's incorrect. So we need to check our work, and again, we need to check in the original equation. So let's check our solution of x being 9. And again, right side for this equation was just 2, so we didn't have to do a whole lot about that. On the left side of the equation, that's where we have to put in our 9 for x. We had log of 9x, or 9 times 9. Already forgotten the question. 9x plus 19, there we go. 9 times 9 plus 19 minus log of x minus 8, or 9 minus 8. Okay, let's see what we get. We have log of 81 plus 19 minus log of 1. 81 plus 19 is 100. And I can say log of 100, that's 10 to what power gives me 100? The answer is the power is 2. Log of 1, 10 to what power gives me 1? The answer is the power is 0. So we have equals to 2. So left side is equal to the right side, and so therefore we can say that 9 definitely is the solution to that equation.